All right, we're back. We're going to be on page 320, but 320 actually starts with a concept from, well, from a lot of pages. And we've just been dealing with it, right? Concave up, concave down, second derivative type things. Let's just go back really quickly. So the most common way that you're going to talk about concavity is probably to be given the graph of f prime, the first derivative, and you can tell from that immediately. So if f prime is increasing, so I'm looking right here, if f prime is increasing, then I know that f of x is concave up. If f prime is decreasing, then I know that f of x is concave down. So what is concave up? Concave up, the tangent lines are below the curve. The derivative, f prime, is increasing. Concave down, the tangent lines are above the curve. The derivative, f prime, is going to be decreasing. So that's the most common way you'll see it. You can tell, I just mentioned it, if you have the graph of f, you can look at where the tangent lines fall. Are they above or below? If they're above, then the graph is concave down. If they're below, then the graph is concave up. So that's if you have the graph of f. And then if we have f double prime, we can tell concavity, because if f double prime is positive, that means f prime is increasing. Both of those mean that f is concave up. If f double prime is negative, then f prime is decreasing. Both of those mean that f is concave down. So there's a lot going on there. And then the points at which the concavity changes are called points of inflection. So we will get a point of inflection. I always forget, like, if I don't pick it up, I can keep going without getting those extra little, like, overlaps versus, so quality. So a point of inflection is just where concavity changes. So that's a very second derivative type thing. So let's see what the actual in the box type definition we have here is. So I want to highlight the box for you. So here we go. Perfect-ish. So the function f of x has a point of inflection at x equals c if the following two things are true. X equals c is in the domain of f of x. So concavity frequently changes at discontinuities because you're just kind of like piecing things together or whatever. So concavity can definitely change at a point not in the domain, but you won't have a point of inflection there because you don't have a point there, right? So x equals c is in the domain of f of x, and f double prime has a sign change. That's all that we need, right? We don't need, so this is a big thing that I see. I'm gonna write it in red here. So you don't need f double prime, let's say of c, doesn't need to be 0. In fact, it's often the case that f double prime of c is not equal to 0. It's often the case that f double prime of c doesn't exist, right? So it's a point in the domain of f of x where f double prime has a sign change. That's all we need is a sign change. One of the most common misconceptions that I see is students will find f double prime, they'll set it equal to 0, they'll get the zeros and they'll be like, oh, these are all points of inflection, which is so weird to me because when you're doing the first derivative test for maximums and minimums, you often see critical points that show up, right? But there's no sign change for the first derivative. So why would you think instantly that every 0 of the second derivative is going to have a sign change? Just not the case, right? So here are two graphs that have points of inflection. So the first one that we're looking at here, let me just highlight some things. So in this particular one, we have that f double prime of 3 is equal to 0. So we don't need the function. I'm just telling you that that's definitely the case. F double prime of 3 is equal to 0. But that's not why we have a point of inflection. We actually have a point of inflection because the curve changes from concave down to concave up, right? That's what causes a point of inflection. So when we look at this second example here, where we are told that f double prime of 3 does not exist. So you can actually tell from this that f double prime of 3 won't exist because f prime of 3 doesn't exist, right? So f prime is not continuous at x equals 3. So how could f double prime exist? But f double prime of 3 does not exist. That is not the reason, however, that we have a point of inflection. The reason that we have a point of inflection is that we are changing from concave up, right? The tangent lines would be below the curve, so concave up, to concave down. That's what we need if we're going to have a point of inflection. So it is not enough for f double prime to equal 0. It is not enough for f double prime to be undefined. What we need is a sign change. It's actually all you need is the sign change. So keep that in mind. Don't get that wrong. It's one of my pet peeves because it seems like something that is such a like small step from the first derivative test to this concept of points of inflection, and yet students just like don't want to latch on to that. So let's see if we can do this. Find the points of inflection and create a sign chart. Well, how are we going to find the points of inflection if we don't create the sign chart? So it should really be create a sign chart for f double prime, then identify the points of inflection. But whatever. I don't know who wrote that question, but they should consider rewriting that. All right, so there's no way to jump straight to f double prime, even though notationally I'm trying to do it. So we're going to get 15x to the fourth minus 20x cubed. Derivative of 1 is 0, so we're good there. F double prime. Okay, so it's going to be 60x cubed minus 60x squared. We should try to factor this. So 60x squared can come out. We're left with x minus 1. Okay, do I think that's right? I think that's right. So that's f double prime. All right, sign chart. There we go. So what's going on our sign chart? This is a sign chart for f double prime, so label it because it starts getting really confusing if you're not labeling your sign charts because you're frequently going to have one for f prime, you have one for f double prime. You might choose to make one for f, but rarely do you do that, but you might, who knows. So 0 and 1 go on here. Okay, so plug in negative a billion, you get negative, anything squared is positive, so a positive and then a negative, so negative. And then, okay, in my mind, I'm thinking 0 comes from here, and that's to the second degree, so there's not going to be a sign change here. But if you're uncomfortable with that, just like pick a value and plug it in. But since it has a multiplicity of 2, and that's even, there won't be a sign change. But whatever, let's test it anyway. So like say 1/2 is between 0 and 1. 1/2 squared is positive. 1/2 minus 1 is negative, so negative again, which we were expecting. But you know, it's kind of reassuring anyway. And then a billion would give us positive. Okay, so we are looking for the sign changes. All right, so the points of inflection. So this says find the points of inflection. Really annoying. Usually the question is find the x coordinate of the point of inflection. So we have our sign chart. I'm going to say that f of x has a, you can abbreviate point of inflection, POI at x equals 1, because we always want to defend our answer. We don't just want to like give an answer. So why does it have a point of inflection? Well, because f double prime of x, I guess, changes sign there. Okay, I don't actually care that it changes from negative to positive. It doesn't make a difference. There aren't like, I've always felt like there should be different names, like a rising point of inflection, a falling point of inflection, or something like that. But I don't think, well, maybe I looked it up once and there is something like that, but it definitely is not a common thing to talk about. There's just points of inflection, right? So all we have is a sign change. We don't care that it goes negative, positive, positive, negative, whatever, sign change. And we got it. But the point of inflection is, I need to find f of 1, which is nice because f of 1 is the second easiest value you could probably find. The easiest one would have been 0, but there wasn't a point of inflection there because there is no sign change in the second derivative. So 3 minus 5 is negative 2, plus 1 is negative 1. So the point of inflection is 1, negative 1. All right, and that answers the question. So let's see what this next one is. All right, so not bad. Let's do it. State all intervals on which f of x is concave down. All right, so we're going to need the second derivative for that. So let's find the second derivative. So f prime, f prime is 1. All right, so I'm thinking of 1 over x as x to the negative first. So I can power rule it, bring down the exponent, negative x to the subtract 1, negative second. So minus x to the negative second. And I'm going to leave it like that until I find the second derivative. Like if I had to do more with this, I would rewrite that probably so that I could actually like deal with it. but I don't need that. So I'm just going to find f double prime, bring down, so the derivative of 1 is 0. Bring down the exponent, I get positive 2 because of the negative that's already hanging out there. Subtract 1, so I get 2x to the negative third. All right. Intervals where the function is concave down. All right, so I can definitely do that. So let's make a sign chart. I'm gonna make my sign chart down here because, whoa, where'd I go? That was weird. I jumped way up. I don't actually know what I hit to make that happen. Seems like it'd be useful to know that. All right, I'm gonna put it down here though, because I'm gonna do way more than this problem is asking for. You might wanna rewrite this as 2 over x cubed, because it's easier when the x is in the denominator to remember, like, oh yeah, so x can't be 0. So 0, plug in a negative, cube it, it stays negative, so that's gonna be negative here. And then plug in a positive, cube it, it's positive, obviously. So we get this. Okay, so where is this thing concave down? So, ooh, I didn't label it. This is for f double prime. Okay. So let's say f of x is concave down for x less than 0. And then the question is why? Why is it concave down? Because f double prime of x is less than 0. There. Okay, that's a good answer. All right, what else might I want to do? The other thing I might want to do, and I'm actually going to move this down even more, is I might want to like just look at where is the function increasing, where's it decreasing, like where's all that stuff happening? So I'm going to take f prime and I'm going to rewrite it. So let's do that. So this is we're done, right? So everything I do from here is going to be extra. So f prime of x is, so it's 1 minus 1 over x squared. So that's x squared minus 1 over x squared, which you can rewrite as x plus 1, x minus 1 over x squared. So the reason I skipped all the steps there is like, this is extra. We don't really need to do it. But I made it 1 minus 1 over x squared. Then a common denominator is x squared. So that's x squared minus 1 over x squared. X squared minus 1 factors into x plus 1, x minus 1. Okay, so let's make a sign chart for f prime. All right, so I need to put -1, 1, and 0 on this, and I want them in like the correct relative positions. Plug in negative a billion, I get negative, negative, positive, negative, negative, so 2 negatives, so positive. So I know that the function is increasing and concave down until I get to -1. That's the kind of thing we want to do. Between, so -1 comes from a first degree factor, so there's going to be a sign change. We could test -1/2, let's say. So that'll be a positive, a negative, a positive, so we get negative. We get the sign change that we're expecting. 0 comes from a factor that has a multiplicity of 2. It's in the denominator, but it doesn't make a difference. So there's not going to be a sign change. But if you want, you can test positive 1/2, and you get positive, negative, positive. So negative, and then a billion is definitely positive. So if you look at it, you can just tell that, so for example, let's choose a region. So let's say f of x is, all right, I'm going to say decreasing concave up. So just looking at the sign chart, can you tell where I'm looking? F of x is decreasing concave up. So I'm going to say decreasing concave up for, or let's say on the interval 0 to 1. And then I want to say why? Because f prime of x is less than 0 and f double prime of x is greater than 0 on that interval. So this is why when I make my sign charts, I put lots of pluses and lots of minuses. It's because I want to make stacked sign charts and I can see each region really clearly as I'm going through it. And that's pretty good. So like, and we could go through and do that for like all the regions. So like from 1 to infinity, f is increasing concave up. From -1 to 0, f is decreasing concave down. And negative infinity to -1, F is increasing, and concave down. So once we know what those shapes look like, we'll be pretty well set up to actually like sketch this thing, find all points of inflection, or explain something else. So there's actually something I kind of glossed over when I put the numbers on the F prime number line. I did not gloss over it for F double prime. F double prime has 0 on the number line because F double prime is undefined there. That's the same reason F prime has 0 on the number line. If you look, x equals 0 is not actually in the domain of the function because the function is this. So x equals 0 is not in the domain. X equals 0 is the only place there's a sign change in the second derivative. So let's say f of x has no points of inflection. So this is a little weird, right? Because there's a sign change in the second derivative, but there's no point of inflection because the only sign change in f double prime of x is what? What was that? What? Go away. That was weird, man. I don't know. Sometimes like the stylus, it like, maybe it goes faster than I go. I don't know. Is at x equals 0, but x equals 0 is not in the domain. The domain of f of x. So the only possible place you could have had a point of inflection isn't in the domain. So there are no points of inflection. So these are all really common things that you'll be doing involving concavity. Identifying points of inflection, almost as common as finding maximums and minimums, a little less common, but almost as common. Finding where something is like increasing and concave up or decreasing and concave up, like that's a big deal. Figuring out why there isn't a point of inflection despite there being a sign change, figuring out why there is a point of inflection despite f double prime not being 0. Like these are all things that you have to think about, and I will be back in the next video to continue thinking about them with you. So I will see you then.